Hello everyone, how are you? At least we have a sunny day in Vancouver. Can you hear me? Okay. I was worried because nobody was answering. Okay, good. So we are almost finished, which is, at least for me, a bit sad. We are all dead and burnt out. Yes, I know. I'm incredibly tired right now. I'm working in different projects at the same time, working with people that is in mainland China. So I'm working on on day and night, and yeah, it's crazy. Okay, so yeah, basically we have only that's last week's Monday. Yes, exactly. Someone is what is sleep? I sleeping when you're doing a PhD is basically non-existent. Yeah, you just sleep 3 or 4 hours. And yeah, the undergrad is also very 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 demanding. Okay, good. So yes, so we only have this lecture and one more, and we finish. So today we will talk about the latest. We'll discuss basically the latest new topic. Give me a second. Good. So we will talk about something called sphere tracing. It's also called ray marching. So ray marching, sphere tracing. Yeah, you'll see why it's called sphere tracing. So the learning goals for today, we will talk about this ray marching or sphere tracing. This is related with volume rendering, with something called sign distance functions that you may already know about this, right, in your math classes, when you have a function that is basically describing a surface. So for example, you can have an implicit function to describe a sphere, right? So there are the implicit versions of spheres, cones, and things like that. Well, that is basically a function that whenever the function is 0, you're basically on the surface. We'll also talk about ray tracing shadows, and I will show you a coding example. That is very important because some people, I understand, you're probably struggling with the ray tracing assignment. So I want to show you an example today. I will actually show you the solution of some parts of the ray tracing assignment, but I will do that to inspire you, right? And you will see that it's probably easier than you think. So I hope you like it. Okay, so let's go on. Somebody said inspire us to copy it all. Don't look at that. Don't think that, please. Okay, so in the last lecture we were talking about the RTX technology, right? So we were saying that this amazing and almost magical thing that is happening in real time, in the end, is just the same algorithms, the same math that we have discussed, right? There is nothing like really new. It's just a bunch of new hardware, a bunch of new processors, right? Very tiny processors, right? And they're in the end they're doing exactly the same as the other techniques. So we have some space partitioning algorithms, some very efficient adaptive ray triangles intersections and adaptive tracing and things like that. And also this concept of denoising that is very related with AI. I mean, it is processed with artificial intelligence. So yeah, I think in my opinion and in the opinion of many people, I think the future of computer graphics, the future of ray tracing in particular, is probably very close to deep learning, because deep learning is very good to basically translate from one type of image to another, and in this case, basically it was. I mean, it's not easy. I mean, it obviously takes a lot of time, right? And it's hard working, of course. But in the end, it is very possible to get a very noisy image and basically train a neural network, a convolutional neural network, to give you the denoising version of this, right? So this has been proved to be very good for ray tracing technologies in real time. There's also a lot of research in super resolution, so you may already know about that. There are a lot of papers of people that are using GAN technology, GAN networks, generic adversarial neural networks, to basically artificially increase the resolution of images. So imagine you have an image that is whatever, like 800 by 800 pixels, and you want to just enlarge that by whatever, like 2000 by 2000. And of course, like before this technology, that was just crazy, right? The way you basically, what you could enlarge an image in Photoshop is just by filling all those empty spaces, right? I mean, you're increasing the size of the image just by averaging the colors of the pixels that are around, right? But that is basically just like blurring the image, right? So that is why, like, the usual increasing of an image, you will not get more detail. However, that is actually possible with artificial intelligence. Of course, the detail that you see in those like super resolution images is fake in some sense, right? It's not the real. So people think that it will be like the movies in which there is like a very pixelated picture of a car and you cannot see the plate, and you will somehow get a neural network enlarge that image and you will see clearly the plate. I mean, that could be possible, but that what will happen is that the neural network will just invent almost random numbers for that plate. It will not be the actual plate, right? So yeah, so basically, yeah, the deep learning is something that it will last for a couple of for many years in computer graphics. So we were talking about this, and of course hardware, right? What these guys are doing is just increase the number of cores, modifying the cores to make them like specialized in a specific computation, and in the end, yeah, you just have like, it's like having just more machines in your computer, and that's why it's just faster, right? And this will keep increasing, right? So I don't know, maybe in 5 years from now, we will see that besides the integer cores and the ray tracing cores and the tensor cores, we'll probably start seeing deep of field cores and glossy reflection cores and things like that, right? I mean, maybe eventually, almost for every possible effect in computer graphics, we will have just a bunch of cores inside these GPUs, and this will be just crazy, right? Okay, so now let's talk about other rendering techniques. So I will show you this video. It is, where is it? Yeah, it's here. So let's look at this video. And please tell me what you think about this. It's trippy. Yes, it's very trippy. But it's beautiful, right? So, what type of geometry do you think is this? I mean, it's 3D, right? This is not a 2D animation. It's obviously 3D. And it's really cool. Yeah, someone is saying, a lot of people are saying fractal. Yes, these are fractals, exactly. But let's talk about the geometry. What type of geometry do you think they are using? Triangles? Voxels? If it's triangles, how many triangles do you think this thing has? How many million triangles or billion triangles? Infinite? Well, of course it can't be infinite, right? If it were triangles, for example, if you see, the shapes are actually changing, right? If you look closer, look at that. The shapes are actually changing. And that is obviously possible with triangles, right? But it means that you need to have some procedural generation of triangles, right? And someone is saying, will the neural engine from Apple M1 chip also improve ray tracing? I don't know. I haven't seen any information. Yeah, I don't know that chip. So yeah, I have no idea. But I mean, I guess. This is very similar to Doctor Strange. Yes, this type of like 3D fractals things. Is exactly, this is the same thing they use for Doctor Strange. That was done by ILM. A couple of friends of mine, they were working on that movie, And also they use the same for Guardians of the Galaxy 2. No, I didn't create this thing. So Guardians of the Galaxy 2, the latest scenes, right? They're like in the castle of this guy, and yeah, basically the ambient is also like a fractal. But so, what do you think? Do you think these are triangles, voxels, or what type of thing? How do you render this thing when with the information you already know? You already know about rasterization and ray tracing, right? So, which rendering technique do you think it's used here? Are you just friends with everyone who has work on my No, not like that. No, the thing is, I have a couple of friends, three friends in particular, that they work in VFX and they have been working on this area for a lot of years. And one of those, he's been working for more than 10 years. They are also from my hometown. They're also Mexicans, and we were friends before. And yeah, it's just yeah. And I have a couple of ex-students also then they are also already working there also. Okay, so yeah, someone is saying ray marching. Yeah, I mean, it's almost obvious, right? Because that's the topic of our lecture today. Yeah. So the thing is, if these were triangles, it could be, but if these were triangles, it would just crazy. The amount of triangles that you would need to generate to create this super intricate geometry. Look at this. It's very intricate, right? You could also fake it with maps, right? You could use opacity maps and things like that, but everything would need to be procedural, and it will be just incredibly hard. So the thing is, these are fractals. And fractals, you can create a fractal as a mathematical function from which you can get a distance, right? Basically a function that could describe a surface whenever the function is equal to 0, right? You can use that type of math to create a fractal. So, keeping that in mind, imagine that we have two shapes in our scene, and these two shapes are not made out of voxels or triangles. I mean, this could also be used for voxels, but let's just remove the voxels from our idea. So let's talk about only implicit surfaces, right, or just functions. So a sine distance function is again a function in which if the function is 0, it means that you are basically in the isosurface, right? But also, because it's sine, it means that when you are outside that function or outside that volume, right, and you get the distance to that function, you will get a positive value if you're outside and a negative value if you're inside. I'm not sure, but I think you might already work with this type of things. Have you ever worked with implicit surfaces or implicit functions, things like that? I guess, right? No? Okay. Don't worry, we will not get deep into this topic in particular. The way you actually construct surfaces using implicit functions, this is part of the geometric processing lectures, right, for Ala Scheffer, and probably in a multivariable calculus, right? But for now, let's just keep learning the computer graphic technique that you can use whenever you have a function like this, right? So let's say that you have these surfaces right here that they're not described using triangles, but you have a function, right? You have a mathematical function that basically tells you the distance to the surface, either in positive or negative values, and if the distance is equal to 0, it means that you are basically on the surface. So we will use some sort of ray tracing, but it's not exactly like the ray tracing we know. So this is called ray marching, or also sphere marching. So how this thing works? So we always start from the origin of the ray. So we have a ray, and we have in the scene, in this case, we have two objects, right? So the way this algorithm works is it works by iterating a possible solution every time. So it's an iteration, it's an iterative algorithm, right? So the first iteration, you compute, you cycle through all the objects on your scene, in this case the sphere and this other function, and you get the closest point to your ray origin. So in this case, the closest point to the origin is this. Let's call this point 1 or P1, right? Again, you get this by just getting the distance between these two functions. So once you have this, you know that there is absolutely no intersection in basically this area, in this radius, right? Or in this sphere, right? I mean, I'm showing this in 2D, but if this is already 3D, this is obviously a sphere, right? So there's nothing in this sphere. It means that you could basically walk or make your ray to travel or to march, right? So basically to walk your ray into this position right here, right? Basically, you just multiply your ray, if it's normalized, right? You just multiply your ray times the ratio, the radius, sorry, of your sphere, and now this will be your next center, right, or your next ray origin, because there's nothing inside the sphere. So once you get there, you basically repeat exactly the same thing. This algorithm is incredibly easy and very easy to implement. It's very elegant. You basically do the same. You cycle through all the objects in the scene. You get the closest point to your ray origin. Now is this guy. There's nothing inside that. And now this will be, you can walk, right, forward, and this will be your next origin. And just keep doing that, finding new closest positions. In this case, now the closest one is not in the blue object, now it's in this guy, right? And the trick here is, when do you terminate your algorithm? Well, basically you define a very small distance or a very small radius, meaning that whenever your sphere is as small as whatever epsilon value you decide, you consider that you're already there, right? Because the thing is, remember, in general, in computer graphics, it will be almost impossible to get the exact position in which a function is equal to 0, right? So you just keep repeating that. In this case, right, you're going in this direction, and these are the closest points. But again, just keep walking on this same direction, right, of your ray. So now this is the next position. Now this is the closest point. You need to keep forward, right? You keep forward again and again and again, and everything gets very tiny. And then at the end, right, whenever you get into the smallest sphere possible, as you define it, you just get into the intersection. And once you have the intersection, that's it. You just ends there, and that is the intersection. It's very similar to, in the end, it's very similar to have the other ray tracing algorithms, right? You can compute a ray to your light to see if you're blocked, if you're in the shadow or not, or things like that. Okay, so let's see. You have a couple of questions. So each object is described by an implicit function, right? Yes. So at each step, you find the minimum value of which each object implicit function gives you 0, which will be the closest object. Yeah, well, yeah, you compute the closest point from your ray origin to those functions, right? The closest point to those functions. It can be pretty, is there an epsilon for this one, epsilon for tolerance? And so many, yeah, it's probably is right. It can be whatever we want, but pretty small. Exactly. Yeah, you define the epsilon. Yeah, again, it can be depending on, sometimes it depends on the scale of your scene and things like that, right? So, because if that value is just very, very small, you're probably just wasting time. When everything is very close, you're probably wasting time. If the objects are very, very, if they are very big and the scene is very big, or the camera is very, I don't know, like very far from the objects, maybe epsilon could, yeah, maybe you don't need like super, super small epsilon, right? And someone is asking why the reason of we are doing this. Well, again, this ray, this is some version of ray tracing. So this version of ray tracing, it could seem that is not better than the other options that we already discussed, right? So when do we need this? Whenever the geometry you want to represent, it is very hard or almost impossible to describe with triangles, right? So that is basically the reason. So one option, one example is the fractals, right? So imagine you have a very easy, not exactly easy, right? But a very straightforward way to describe a very complex fractal with a function, with a mathematical function. If you want to render that with traditional techniques, now you have the enormous problem of somehow translating that function into triangles. That is incredibly hard. That is basically something in computer graphics we call surface reconstruction, which is basically like creating triangles, procedurally creating triangles for that surface that could be incredibly complicated, like very intricate, like the one we saw. And so that will be very hard, right? So instead of just using triangles, you can use this algorithm and it will be way cheaper. So let me show you another example of this. You can achieve incredibly incredible things. Give me a second because... So here's another... Oh, I guess it's not working because I'm sharing my screen. I don't know. This should be working. Give me a second. Yes. So this is a fractal. This is being rendered in real time in my graphics card. Look at this geometry. I mean, procedurally creating this geometry with triangles would be crazy. This could be 10 million triangles, right? So that is absolutely just is crazy. And it is even rendered in real time. And by the way, if you haven't seen Shader Toy, this is a very nice website. You can this is basically a website in which people can share shaders and basically work with like different computer graphics techniques. It's very nice. It was created by two computer engineers, computer scientists from, I think both are from Spain, and one of those is Inigo Quiles, and the other one, I don't remember his name, but the other one is the lead. I think this is the lead render engineer from Pixar. These guys are amazing. I don't know these guys in person, but these guys are impressive. So yeah, this is the type of things that you can do. Questions? No, I'm not. They're not my friends. Someone is saying, "Damn, your friends." No, they're not. I wish, but they're not my friends. So it is. Is it clear when do we need to use this? Because again, I mean, ray marching or sphere tracing is not for everything, right? I mean, if you want to use this with a simple triangle scene, it will just crazy. It will be incredibly expensive. Okay, so now, sorry, could you give us an example of an implicit function? Okay, yeah, give me a second. I think so. I mean, in general, you will see. So, for example, if you go to Wikipedia, you will see a couple of examples. Yes, give me a second. Implicit functions. I'm opening. How much different in terms of runtime complexity is this compared to ray tracing? Again, depending on the scene. If the scene is the typical scene, you would use triangles. So if you don't have like a crazy amount of triangles, things like that, this will be very expensive. If it's exactly the opposite, if you have a super intricate surface that is described by a function, it will be incredibly cheaper compared with the triangle option. I don't remember right now the exact like the complexity of the algorithm, but yeah, it's again depends of what you use. So for example here, yes, so here are a couple of examples. Where are the examples? I remember that there were examples here. I mean, implicit function for a sphere, for example, is what? X squared plus y squared plus z squared equals 0, I guess. Yes, that could be an example. But again, I'm not going deep into that topic because that topic of like literally describing surfaces with those type of functions is not a topic for this thing. It's just we needed to see this as a ray tracing technique, right? Okay, So I would recommend you to check out this video. This is a very nice video. This is from Martin. I don't remember how to pronounce his name. Steinrocken. And he's actually showing an example of like literally coding a ray marching algorithm for simple objects as a sphere, torus, cones, and things like that. So you could actually use that and get inspired by his code, because he's actually using a shader toy to, for example, do the possible extra things for the ray tracing assignment, right? So remember, one of the bonus things we have is to include a cone or include a torus. There is a way to compute, right? There is a way to compute the intersection between a ray and a torus, for example, which is a bit complicated. So another way to do it is to use the implicit version of a torus and compute the closest point from your ray and that torus, and basically use ray marching or sphere marching. So you could also implement that in your bonus if you want, and that is obviously optional. Okay, so now I want to show you, because we already have half an hour already, and again, sorry that I insist, but I got, I think, 2 or 3 emails from the department already telling me that I need to tell you, I need to insist that you should please answer these student evaluation of teaching survey. So if you haven't had time to do it, please do it. We really need that. I think at this time, because we are also giving the lectures in this pandemic version, online, things like that, it is very important for the department to have your feedback. So yes, please take, if you can do it, please take the time, because also, yeah, someone is saying survey should be board mandatory. Maybe it should, but I think, but I cannot do it mandatory, and the department is never said that, so it's not mandatory, it's optional. But it's just, we are just asking you this favor. I don't know how much time it will take you. I don't know if it's 10 minutes, 15 minutes, I have no idea. But if you have time, please do it. I will probably even like send an email later, a personal email to everyone, just reminding, because I think that's, so far we have only 30 responses or something like that. And we have more than 100 students. Okay, so now has a question. Yes. Give me a second.
Hi, let me see if I can accurately summarize the point about sign distance function and ray marching.
Okay.
So you're saying in scenarios like where fractals are used, there are implicit equations that you can set up to essentially create geometric boundaries on the three-dimensional Euclidean space.
Yeah.
And when you do the sign distance ray marching, you're saying you actually have to solve an optimization problem where you get the intersection between a norm ball around your current origin of ray and the nearest point of the object in the 3D space. Is that a correct impression?
No, you're not computing an intersection. You just compute a distance. You compute
Right.
the closest point, or the closest distance from your ray origin to your function. The thing is, implicit. Yeah. So give me a sec. So the thing that this type of functions in the end will give you a distance field. Okay. So a distance field will look like a gradient. I think I have an image. Give me a second. I think I can. Give me a second. I have an image here that is not mine. This is from Scratch Pixel, but yeah, I think this could be helpful. Can you see the image?
I see.
So for example,
this
is the implicit function of a sphere, right? Of not a sphere, actually a circle. So this is basically what you get. It's like it's like a gradient, right? So basically, whenever you so imagine that I'm here, right? Basically, my ray is basically starting here. If I am here, I will get the value, a value that is basically the distance from that point to the surface. So I'm not computing. I'm not computing the intersection to the surface. I'm just computing the distance, right? So having that distance, right, I just increase my sphere now my sphere will have that distance as radius, right? And I know that there's absolutely nothing inside that sphere that is basically blocking me, right? And I
Right.
can walk, right?
Yeah, so you're saying for each object you need to store, I guess, at least the equations about the boundary of the object and the equations about the distance field
Yes.
from the boundaries. But as long as you have that information, basically you can compute distances in
Yeah.
constant time.
Yes. Exactly. Yeah.
Okay.
Yeah. Exactly. Okay. So now we can continue with the shadow example. I really want to do this, and again, I will probably give you a couple of points literally for free, but I think it's worth it for some of you that are, if some of you are really struggling with the ray tracing assignment. I've received some private messages, and I think some people is trying to sometimes like solving a couple of things like in a very sophisticated way, maybe wasting a lot of time, and I want to show you that it could be easier. Okay, so this is the code, or this is a yeah. So this is a code from inspired obviously in Peter Shirley's code. This is, I think, if I'm not, I think this is up to chapter 8, chapter 7. So this is in the very early stages of the code, right? Like chapter 7 kind of. And this is basically the image you get. I think at this point a lot of people already have something like this, or you're maybe already ahead of that. But I want to show you the example of how to compute shadows. Maybe for a lot of people, computing shadows was very easy already, and people is like, oh my god, that is super easy. But some people was not that easy probably. So I want to show you how you could do it. Okay, so let's talk a little bit about that. So this function right here, the color function here, it has this if statement. Give me a second, and increase this. Can you read the code? Say yes if you can read the code. Okay. So basically, this hit statement, if statement, sorry, is basically checking if the ray is basically hitting something in the world, right? And if it's hitting something, it will basically it will behave as a recursive algorithm, right? Because it will basically return this value 0.5 times a new calling for this function, right? So it will be basically call this thing again. And this is because this is a path tracing. Remember, this is not actually a ray tracing. It's not computing the color in the first intersection. It is getting the first intersection, and from there it's just bouncing and bouncing and bouncing the ray. And by the way, I will have a lot of questions for you today to see if you understand the code. How is the termination of this code? Where does this recursive path tracing terminates? Does it have a depth ray? What do you think? The depth equals 0. You sure? I mean, this version. When the ray doesn't hit anything. Exactly. Thank you. So this version, at least, I don't remember if if at the end of the book a depth ray is implemented. I honestly don't remember right now. But in this stage of the code, yeah, it basically terminates when it's not hitting anything, right? So it just keep bouncing, 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 and bouncing. It will hit everything. So my first question for you is, what this 0.5 means. What do you think is this? 0.5. Why I'm multiplying this recursive color by 0.5? What is this? And by the way, yes. So for example, if it's not hitting anything, right? If basically it's just going through the sky, then it will get into this else, and it will just return the color of the sky, right? Reducing, someone is saying attenuation of each bounce. Exactly, it's an attenuation of each bounce. It's basically defining how much each bounce is contributing to the color. You agree? Right? So for example, what happens if I modify this and say that is 1.0? We can actually test it. What do you think it will look? I will run my code. And by the way, again, this is almost the same code from Per Shirley. The only thing I've changed is I've added a very dirty OMP parallelization. But yeah, other than that, it's basically the same code. I can talk about the parallelization later. So let me just open the image. So how do you think? How the image will look if I use 1.0? What will be the color of my objects? What do you think? Okay, some people is saying darker. Okay. Background color, yes. It will be almost the same as the background color. Because basically what is happening here, actually it will be the background color. Because what is happening here is that the ray is basically bouncing, right? But every time it's bouncing, it's getting the color by recursively sending another ray. It will basically stop whenever it gets to the sky. So when it gets to the sky, that color will be literally the color of the sky, right? The certain grade of blue, right? But I'm multiplying that color times 1.0. So there is no attenuation. There is no absorption of light in my surfaces. So another way to see this number, right, is also kind of like, it's like faking how the surfaces are basically absorbing some of the color. So the bounce is basically, right, like the light, is bouncing into the surfaces, and some of the light will basically bounce and in real life, and some of the light will basically get absorbed. So, right? So if I said 0.5 is somehow, conceptually speaking, is somehow like saying I will absorb half of the light, right? And the rest will basically bounce, right? Okay, so I hope this is clear. Okay, so what do we need to compute the shadow? And by the way, I would like to see, like, how many lines of code do you think we need to compute the shadows? In the range of 20-ish, 30, 50, 100, less than 5. So I would like to give me your prediction. Okay, so someone is saying less than 5, 5 to 10, 10. It's either 5 or 500. Okay, so the first thing is we need a light position, right? So let's say vec3 light position. I hope not making any mistake. Okay, so I will create a vec3 for the light position. Let me see what is the position of the spheres here. 0, 0. Okay, so it could be 20, 5, whatever. I mean, for now it just could be almost any position, right? So we need a light position. Then we need to compute a shadow ray. You agree? So basically, if we are inside this if, we are hitting something, right? And that hitting or that intersection is recorded here. So rec P is basically the intersection, right? So we need to create a ray right? So the function ray, I think it takes a position, which in this case will be, so the origin of the ray will be the intersection. So rec.p, yeah. And then how can I create the shadow ray? Can you tell me? Yes, we are talking about ray tracing shadows, yes. So how can so what is basically the shadow ray? We need to send the ray to the light, exactly. So I'm already a light position. It's already there. So what do you think? How do I compute the vector? Is the intersection minus the light position or the light position minus? Yes, so someone is already answering. Thank you so much. Yes, it's the light position. So light position minus rec dot p. You agree? Sorry. Yes. You agree with this? Good. Now we need to compute the intersection, and the thing is that is already there in it's already given in the code, right? I mean, this line right here, it basically computes if a given ray is intersecting with something on the world, right? So I can literally copy this. I could, right? So let's say, sorry, let's say, so so basically if I hit something in the world, the thing is I just need to change the ray, right? So instead of R will be shadow ray. You agree? Right? This I can leave the same. This is the min. This is the max value, max value, so that it can be the same. This can be the same, right? So basically this line of code is just checking if that shadow ray is hitting something. You agree? It's just checking if it's hitting something. So let's say for now that, let's say that if I don't hit something, I basically compute this, right? Which is basically the previous lines of code, right? And if I hit something, it means that I'm in shadow. And for now, I'll just return, I will return black, probably. Yes. Deck 3, so it will be right? Let's see. Yes. Okay, so let's see. So let me save it. Let's run it. And it's processing, computing, 97, 99%. Done. Okay. So let's see the image. Sorry. Let me reload. Every time I need to reload this thing. Okay, so let's see the image. Yes! So we have shadows. We have ray tree shadows. Good. Somebody's saying, it is possible to share this code online like on GitHub or something for a reference? No. I'm already showing the code. I mean, it's all just a few lines of code. No. I will not share. I mean, it's there. We are seeing this, and yeah, it will be basically recorded on the video also, right? Okay, so we have shadows. That's it, right? We're just sending another ray into the light, right, and checking if it's hitting something. But this is horrible, right? This is horrible. And so Paul is asking, why is bottom half black? Well, because this half of the sphere is basically blocked from the light, right? It is blocked from the light, this half of the sphere, right? You agree? I mean, the light is in this direction, right? So the light is just hitting this area of the light of the sphere, right? So everything else is basically in shadow, right? The thing is, this is horrible, right? Because the shadow is it's just black. It's just horrible. So instead of that, let's do something different. We said that this number here, it's like the contribution for each bounce, or it's also the attenuation, right? So let's do something. Let's create a float variable as contribution equals to 0.5, sorry, 0.5. And let's say that I will modify this. So instead of returning a different color, I will get this guy again outside. I hope not making a mistake here. Okay, so I will get this guy outside. Instead of this 0.5, I will get this contribution, which is 0.5. So so what if we hit something, I can modify the contribution. I will basically, the thing is, this 0.5, it's just multiplying the color every time, right? The color you get every time you just bounce, right? So in that sense, because it's attenuating the color, it's just also like decreasing the color, right? So if we hit something, if we just decrease that contribution, it means that for every intersection we get with a ray that is behind the, because it's basically in a shadow, I'm just artificially getting the color, making the colors darker by just reducing its contribution. And again, I think this should work. So bear with me. Let's try it. But you understand what I did? Let's see what happens. Just taking time. Okay. So let's remove this guy. And let's see. Look. Now it's not totally black, right? I'm just modifying the contribution. So now just those areas, it's like, I mean, conceptually speaking, in terms of like simulating how light behaves, this is wrong, right? Because it's not, it is conceptually speaking, what I'm doing here is I'm saying that when a surface is under shadow, it will absorb more light, right? Because also that number is, conceptually speaking, is also somehow defining how much light is basically absorbed by the materials, because it's reducing its contribution. So that is obviously incorrect in terms of physics. But we are not physicists, and in computer graphics, we don't do physics. We are just faking things, right? So in the end, mathematically speaking, we are just decreasing the value of the color. We can do this. And look at this very nice thing. We are still having the effect of the global illumination along with the shadow, right? So we have a source of light, right? And obviously everything here is in shadow, but we have this effect of global illumination, right? That the light is also coming from other parts of the sky, and that is why we still have this I mean, it's very grainy, right? But this like soft shadow here. So, and yeah, I mean, this could be even in a single line of code. Maybe it's not necessary to have something like this. Okay, so now so everybody understand what I did? Ish, yes. Okay, Tommy, if you're saying ish, do you have a question? Okay, I guess not. Understand better when. Okay, okay. So we already have shadows, right? The shadows actually, it's part of your assignment. So I'm already give you like 15 points for free. Okay, so what about soft shadows? How do we compute soft shadows? What do we need to do to compute soft shadows? Remember, or area shadows? What should be different? Can anyone tell me? Yes, area light. So someone is saying we can also reduce the contribution if semi contribution multiple lights. Yes, one option is to create multiple lights, an array of light position. Yes, although I think we actually discussed in the lectures that the way we usually compute the area shadows or soft shadows is not by just cloning the light, but just when you send your shadow ray, instead of using the original position of your light, you can just randomize the position of your light, right? And that will create the illusion that you are that you have an actual shape, or I don't know, a sphere as light, right? You're basically creating an area of light, right? Yeah, randomized within an area or within a sphere or whatever, right? But in the end, if instead of using the same position for the light for all the shadow rays that you're sending, right? Every position here, right, on the floor, for example, it's sending that ray exactly to the same position, right? So if I randomize the position of my light, right, I could probably, not probably, I could, right, because I'm in the end I will basically average everything. I will get a different value. So by averaging the results, some areas will have more chance to get into I don't know, to a place that is not under shadow, right? You remember that? It's on the lectures. I mean, I will not repeat that, but we already discussed that on the lectures. So let's try to do that. We will need to modify this position randomly, okay? And the thing is, we need to send a bunch of new rays. So that is the basic idea of the algorithm. That instead of sending a single ray, right now I'm sending a single ray, right? So instead of sending a single ray, I will need to send a lot of rays, maybe whatever, 20, 30, 50, or whatever number of rays. And for every ray, I will need to use a different shadow, basically a different shadow ray, because the light position will change. So I basically need to change this. So one option is to create a for loop here, right? So basically getting this inside a for loop and saying, okay, just repeat this thing for whatever, 50 times, right? And just average the values. That is one option. But there's another option. So if you remember, this code is already doing some scattering, ray scattering technique, because at this point of the tutorial, and I think everybody will understand this part, at this part of the tutorial, they're already doing the anti-aliasing, right? So can someone remember what is the anti-aliasing technique that is used in this code? Is super sampling or multi-sampling? Multi-sampling, yes. It's multi-sampling, right? So we have this value here, ns. Ns is the number of, which in this case is 100, is the number of rays that are sending randomly for each pixel. So instead of sending 1 ray per pixel, we are actually sending 100 rays per pixel, right? That is actually creating a scattering technique, sending a lot of rays. So if we are already sending multiple rays per pixel, instead of now sending a multiple shadow rays every time we hit something, and that will be basically multiplied by these 100, we can just directly use a random position for the light position, meaning that for every one of these 100 rays that we're sending for each pixel, the light position could be different, meaning that we can basically fake this area shadow, right? So how can we randomize the position of the light? What do you think? Someone can give me an insight? I think we can actually use something that is already here in the code, because again, the code already has something that is giving you a random position, random in unit spheres. Yes, thank you, George. Exactly. So we already have this function here that basically generates random positions in a unit sphere. So if I take my original position, right, so I will say light pos equals to this plus this function. I'm just adding to my original position, I'm just adding a random position in a unit sphere, right? Let's try that. What do you think? It will work? Basically, for every one of these 100 rays, right, the light position will change randomly, okay? So this was our previous render. Let me just duplicate to see the difference, and I will just hit render. You're almost finished the class. Sorry, it's already 3:54, but we're almost done. Okay, so it's computing. computing. Okay, it's done. So let's see. There you go. See? Now the edge, right? Now it's a bit softer, right? Because for the guy, everything that is inside, right, it will not get any chance to not being covered on the shadow. But for the parts that are basically on the border, because we are randomizing the position of the light, some of those are actually will have actually the chance of not getting covered. So can someone tell me how could I increase the radius of my light? So how can I increase the area of my light? Times k, yes. So because I mean this is a random position in a unit sphere, right? So if it's basically this is a yeah, so I can just take this guy and multiply this times whatever 6.0. I have no idea if this will be enough. And let me just increase this number because my image was already very grainy. And let's see how it looks. Let's see. And we can end the lecture with that. Obviously, it will take more time. And let me just create a new. And I have another question for you. What is the making the sphere bigger? Exactly, yeah, making the sphere bigger. Making the sphere of random positions bigger, yes. What type of light I'm using right now? Conceptually speaking, this is a directional light or a point light? What do you think? Can you tell me? Point, exactly. Think about it, the difference, the things that you need to change in this code to use now directional light is just almost nonsense, right? It's very simple. Okay, so let's see. There you go. Look at those beautiful area shadows. Yeah. See? That's it. So we end up with 4 lines of code. Okay? So I'm not saying that everything on your ray tracing assignment will take 4 lines of code. Of course not. But everything that you need to implement, don't just rush to create super sophisticated classes and things like that. Like, okay, I need to create shadows. I need a class for shadows. I need a class for area lights. Just see the lectures, calm down, and you will see that some of those things are actually probably easier. It will take less time to solve, and yeah. So for example, if you compute, later you compute the Boolean or Fonga thing, instead of, I mean, right here I'm just using this probably very dirty trick of just of modifying the contribution of my light to fake the effect of the shadow, right? But we know that if you will compute, for example, the Boolean equation, it means that inside this if statement, instead of modifying the contribution, you will need to just, like in that case, for example, just drop the specular and diffuse level, right? So you just get the ambient color, things like that, right? So yeah, okay, good. So I think we can end here. So thank you so much, and I will see you on Wednesday for our final class. Thank you, everybody. Bye.